Alright guys, we're back here with another stats tutorial. This time we're tackling the topic of hypothesis testing. This is actually a super helpful topic if you go on to do research in your later undergraduate studies or when you go to graduate school. This will be a large part of collecting data and testing hypotheses. If that's not in your future, well, probably at some point in your studies you're going to have to read research studies, and this kind of stuff is oftentimes found in lots of different fields of research. So understanding what a hypothesis is, how to test a hypothesis, and just having an understanding of those topics will help you better understand different articles you read for whatever discipline you're studying. Okay, so let's see what we're trying to tackle here. It says, according to Forbes, the average starting salary of all 2014 college grads was $49,404. Suppose a more recent 2016 study found that in a sample of 40 recent college grads, the average starting salary was $41,250. Assume that the population of all such salaries is approximately normal with a standard deviation of 3,650. Can we conclude that the average starting salary of all recent college grads has increased? Now, you may say to me, well, duh, the recent figure says 41,250 and the old figure says 39,405. Well, yes, obviously the more recent one's higher, but the big difference is that 2014 figure, that is a population figure. It says the average starting salary of all college grads. So there was some sort of research done, and that was established in 2014. Now, in 2016, researchers took a small sample of 40 recent grads. So they didn't talk to every possible recent college grad. They spoke to 40 and found that that starting salary of those 40 students, recent students, was on average $41,250. So what we want to do here is see, is there a trend? That is the $41,250, is that the new normal? Or did those 40 people that happened to speak to the researchers, did they just all randomly have higher salaries? And so it made it look like the average had increased by about $2,000 or so. Okay? Well, that's what the goal of hypothesis testing is to see what's actually going on. Okay? Now, the first step of hypothesis testing is to state your two hypotheses. Now, your two hypotheses are the null hypothesis and the alternative hypothesis. Okay, those are abbreviated as H naught and H1. Okay. Sometimes you see this written as H with the subscript A. When they do that, I sometimes like to use that notation because people say the first step is ho-ha. That is, state H sub 0. Well, they pronounce it as ho to help you remember. And the alternative hypothesis is H sub A, and they say ha. So ho-ha, that's your first step. Other times it's labeled as H sub 0 and H sub 1. Okay, means the exact same thing. That is step 1. That is, state your hypotheses. Now, what is the null hypothesis? Okay, and I'll just label those. That is the null hypothesis. Okay, and this is the alternative hypothesis. hypothesis. Okay? Now, the null hypothesis, that's like the status quo. That's what we know to be true based on prior research. In this case, that is that the starting salary, the average starting salary of college grads is $39,405. So here we say the null hypothesis, and again we will abbreviate that H sub 0, H naught. Oh, I shouldn't put equals there. Put this like that. Is that mu, the population mean, equals 39,405. Yeah, it's dollars, but we won't worry about that right now. Okay. Now, the alternative hypothesis, that is we're not trying to test it, so we're not going to say test, but that's what the alternative to the null hypothesis here. So the null is that the mean now is the same as the mean back in 2014. But what we're asked to consider here, to explore, is did the salary go up? So the alternative hypothesis here, so that is H. Now it's either sub 1 or sub A, and I keep putting an equal sign there. Put a colon, or semicolon, sorry. That is that the mean is actually greater than 39,405. I mean, that's what it looks like. I mean, we don't know for sure, but it looks like it. Now, it's our job to figure out if that is actually the case or not. Okay, so there are our two hypotheses. So you have the null hypothesis, that's the status quo. Okay, that's the way I like to think of it. Status quo. You know, nothing's going on. It's actually the case that that the starting salary is still $39,405 on average. It just happened to be that we got lucky, or the researchers got lucky, when they picked that sample of 40 recent grads and took the average of their salaries, that it happened to be $41,250. Okay, so that was just pure random chance due to sampling error. Okay, so those are our two hypotheses. Yeah, the null hypothesis and the alternative hypothesis. Okay, that's step one. Now, step two is going to be to select the appropriate distribution. This is a pretty easy step right here. Okay? Now, again, select your distribution. Now, here's the way to tell which distribution you're going to use. As far as we're concerned here now, it seems like every time you say a hard, fast rule, there's a situation where that's not the case. But for our purposes in this class, we're doing one chapter of hypothesis testing. If you know the population standard deviation, we're going to use a z-test. We're going to use the z-chart. Okay. Later on, we'll talk about this in class. I'll do another video. If you don't know the population standard deviation, if you don't know sigma, we'll use a t-test. Okay, but we happen to here know, again, look up here, it says the population of all such salaries is approximately normal with a standard deviation of 3,650. So that tells us up here for sure that sigma equals 3,650. So since we know sigma, we're going to use the z distribution. So use the z table since we know sigma. Okay? That's going to be the differentiation, at least for us in this course. Okay? That's step two. That's the easy step. Now, step three is to determine the rejection region based on the significance significance level of the test. Now, I actually didn't, when I was writing that question up there, I didn't give us a significance. So I'm just going to pick one here. Again, when you're doing your homework, when you're doing a test, that significance level is going to be given to you. So I'm just going to pick one here. Typically, they're like, 0.1, 0.05. Sometimes they get bigger than that. But those are the most common ones. So I'm going to say let alpha equal, let's say 0.05. That's a common one. Alpha, that is your significance level. Okay? Now, we need to use this alpha to determine the rejection region. Now, so that means we need to draw a picture here. Okay? It's called the Null model. So I'm going to go over here and I'm going to draw a null model. Okay? So sketch a distribution, a normal distribution. So I'm going to try to make it kind of big. Okay, obviously that's not perfect, but it works. Okay, you get the idea. Okay. All right. So let's see here. We want to sketch a picture of kind of like what's going on if the null hypothesis is true. Okay. Again, it's called the null model. So if the null hypothesis is true, well, right there in the middle, you have the mean, which if the null hypothesis is true, it's 39,405. Okay? Now, we want to draw our rejection regions. Now, the rejection regions are determined by alpha. And here, alpha is 0.05. Now, we haven't discussed the idea of two-tail versus one-tail versus left or right test. Okay, so here's the quick explanation. If you're testing to see if your alternative, you're not testing, if your alternative hypothesis has a less than or equal to, a less than or a greater than sign, that means you're trying to figure out if the sample mean in this case actually is greater than the population. Okay? Or in other cases, maybe it's less than. That's going to involve a one-tail test. You're just concerned with one side of the distribution. Now, in other examples, and we'll do some of these in class, and maybe I'll post a video about them, is if you have if you're just trying to test, if you're just trying to see if the sample mean is just simply different than the population mean, that is, it could be less than or could be greater than, then you use a two-tail test. Okay, but here we only have a one-tail test because we're seeing here our alternative hypothesis has a greater than sign. So we are only concerned with a one-tail test, and since it's greater than, it's going to be a right-handed one-tail test. And this level of significance over here, alpha equals 0.05, that means we are looking, that's going to define our rejection region, and what we are doing here is going to be to separate this null model based on 0.05. That means that 5% or 0.05 of the area under the curve is shaded here, and so that 95% of the area is not shaded at this point. Okay, and we want to also find this z value here. Okay. Now we've had plenty of experience finding z in that situation. Okay, we did that with confidence intervals. We did that with just in chapter 6 when we were just starting to learn the z table to begin with. So we've been doing that a lot. So let's use the z table in the back of the book, or use your calculator to find this z-value. Now, when we're talking about a null model and trying to define a rejection region, this z-value has a special name. It's called a critical z-value. So I'm going to label that z sub crit for z critical. Okay. Now, so we want to find the z-value such that to the left of z there is, well, 1 minus 0.05 area under the curve. So there's 0.95 area under the curve. Now, if you remember that value, that's great. We memorized, or some of us memorized those when we were doing confidence intervals. If not, it's easy, really easy to find using the chart in the back of the book, or you can use your calculator. With the, like, if you have a TI calculator, you'd be using the inverse norm function with 0.95 in the argument, and it looks like that z-value is 1.64. So our critical z-value is 1.64. Okay, so alpha equals 0.05, that's the shaded part over here, and our critical z-value is 1.64. That is our null model. Okay, this is kind of like what's going on if the null hypothesis is true. Now, let's think about this. If the null hypothesis is true, that means if we took just tons and tons and tons of random samples of size 40, then we would usually get a result around 39,405. Okay, sometimes it would be a little bit above, sometimes it would be a little bit below, sometimes it would be, very few times, very rarely it would be way below or way above. Typically it's going to be right around 39,405. Okay, again, that depends on your standard deviation, and we all remember the empirical rule and how much data lies within one standard deviation, 2 standard deviations, that kind of stuff. So, but just think about this being what the distribution would look like if the null hypothesis was true. Okay, so that is step 3. So we've defined our rejection region. This shaded part right there, I guess I haven't really talked about that term specifically, but that shaded part, that is our rejection region. Okay. Turns out we are going to reject the null hypothesis if our calculated test statistic falls in this shaded area. And there's 2 different ways to determine that. One way I think is easier, the other way works just fine, but there's one way I prefer, but I'll show you both ways. Okay, so again, null model, and the shaded part is our rejection region. Now, step 4 is to calculate the test statistic. Okay, specifically for us, that in this example, that's a z-value. Okay, the z-value that corresponds to our sample mean of 41,250. Okay. Now, if we're using the t-distribution, like later on when we don't know sigma, we'll be finding a t-value. If you were doing something called analysis of the variance, you'd be computing an f-value. There's lots of different stats tests where you use different distributions. But for us, we're going to use either z or t, and if you know sigma, we'll be using z. Okay, so we need to calculate z. Now, everybody remembers we've been using z values a lot now. Remember, z equals x bar minus mu over sigma sub x bar, the standard error. It's the standard deviation of the sampling distribution. Okay, so what is a z equal in this instance? So let's fill in all the stuff we know. We know that x bar, that is the sample mean, is 41,250. subtract off mu, that was 39,405. Then you divide by the standard error. Now again, the standard error, that's not just sigma, that's sigma divided by the square root of n. So sigma here is 3,650 divided by the square root of n. Now n, that's our sample size, is 40. So square root of 40. Okay, now be careful, always mind your order of operations here when you use your calculator to figure out what z equals. So I'm going to key it in real fast. 41,250 minus 39,405. We get 1,845, but then we need to divide by the standard error. So divide by, now this is where you want to use parentheses for sure, 3,650 divided by the square root of 40. Okay, and I get 3.19. Okay, actually 3.1969 and change. Now, what do we need to round this to? Now, remember, z value is always rounded to 2 decimal places. That's just because what your book uses, and so we'll use that convention. So if we round to 2 decimal places, it's actually 3.20. Okay, that's our test statistic. The proper name there, that is z sub observed, or maybe z obtained. I've seen both things, both conventions used. We'll say OBS for observed. So z observed is 3.20. Okay? Now, here's another thing we want to talk about. This is going to lead in to step 5, but let's go ahead and talk about it. We want to know, since this, again, we're talking about a one-tail test, we want to know, or even if it was a two-tail test, we'll get into the differences here. We want to know what is the area at or beyond a z value of 3.2. Okay? We want to know what the probability of a z value of 3.2 occurring or something more extreme. Okay? So that's where either your calculator comes into play or using the z-chart in the back of the book. Now, if you're going to use the z-chart in the back of the book, it's probably easier to say, instead of the area to the right of 3.2, it's going to be easier to say what is the area to the left of a z value of negative 3.2, because the way our particular chart is set up in the back of our book is that you're always looking at the area to the left of z. So I'll look that up now, and let's see here. The area to the left of a z value of negative 3.2 is 0.0007. Okay, now we're calling that a p-value. Okay, so the p-value is 0.0007. That's the probability of obtaining a z-score of 3.2 or higher, assuming, the probability of finding a z-value of 0.000, of 3.2, assuming the null hypothesis is true. Okay. Now here is the kicker here, and this is going to feed into the feed into the fifth step here. Okay, so we have a observed z-value and we have a corresponding p-value. Okay, so let's move on to step 5. Step 5 is make a decision. I'm still not very good at writing this yet. Okay, make a decision. Okay, so let's see. I'm going to scroll down, give us a little more room. Okay, I think we have all the information we need there. Okay, so here's how you make a decision. There's two different ways. There's one way, it's called the p-value way. Or the critical value way. So here's the difference. Now they're different sides of the same coin, but let's just go ahead and explain it. Okay, you reject the null hypothesis. Again, we're only testing the null hypothesis. You either reject the null hypothesis or you fail to reject the null hypothesis. And here is the criteria for rejecting the null hypothesis. If P is less than alpha, we reject. Reject the null. Okay? Now, the other side of that coin is if Z observed is greater than Z crit, we reject the null. Okay, let's go back up here to our picture and let's talk about that. So here's our null model. If I plot my observed Z value, that's 3.2. So let's just go ahead and draw that right there and say that is 3. Oh, that's not very good. It's right on the edge here. It actually would be further out, but since my screen only goes so far, we'll have just to make do. That is Z observed. Okay, it's 3.2. You see how that falls in our rejection region? Okay. What we're talking about here is that result 3.20 is pretty unlikely given that the null model is true. It's 3 standard deviations above the mean. Actually, it's 3.2 standard deviations above the mean, which would mean it's a very unlikely result. Okay. Now the threshold we set was 5%, an alpha level of 5%, 0.05, and we said, which corresponded to a Z critical value of 1.64. So any Z critical value above 1.64, which 3.2 certainly is, falls in our rejection region. Likewise, if I shaded the area to the left of 3.2, so in green, shaded that little bit of area, that little bit of area is the p-value of 0.0007. Okay, that's that little bitty bit of area. And I'm exaggerating here because it's actually much less than that. That's the area that in this case is shaded blue and green. Okay, and you see here that the probability to the left of 3.2 is certainly less than the probability to the left of 1.64. So that's where we go down here, is that if the p-value is less than alpha, so in this case we have 0.0007 certainly is less than 0.05. So we reject the null. I like to talk about observed Z values, or if you go to T values. That's just the way I prefer, personal preference. Okay, and you can see the Z observed is, in our case, 3.2, which is certainly greater than the critical value of 1.64. Since that is the case, again, we reject the null hypothesis. Okay, again, what this is saying here is the probability of obtaining a z-score. In this case, a z-score represents a dollar figure of 41,250. So the chance of obtaining that that average salary, given a sample size of 40 and a mean of 39,405, that probability of getting that average salary is 0.0007, which is very, 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 very unlikely. Since it's very unlikely, we conclude that the null model probably isn't correct, because we would only expect what fraction? I mean, what fraction is that? That's what, 7 out of 7 out of 10,000. So 7 out of 10,000. For only 7 out of 10,000 samples, we would expect to find an average starting salary of 41,250. So since that's so unlikely, we say we reject the null hypothesis. There's probably been a change in the starting average salary of recent college grads. And so we say we reject the null hypothesis. That is H sub 0, or if you prefer, H sub 0. We reject the null hypothesis. So it appears that the alternative hypothesis is better at explaining the observed sample, the recent sample. Okay, you can't read that at all. Recent sample. That is, we think there must have been a change. Okay, obviously things like inflation, in general, wage inflation more specifically, should indicate that the salary goes up. But we have shown, according to statistics and the normal distribution, that that finding that that sample of 40 folks where the average starting salary was 41,250, that wasn't just a fluke. Okay, that there was actually something there, and you couldn't have reached that conclusion without doing this the hypothesis testing. Again, you could certainly guess that, oh yeah, sure, it's higher, but you don't know for sure until you test the hypothesis using this essentially this method. Okay. Again, just to review, what we did here is we looked at the text. We first step was that we stated our null hypothesis. That's what we were wanting to see, if the salary of recent grads had increased, but the status quo, what we had recently found to be true, was that the average starting salary was 39,405. Okay, so that is our null hypothesis, H sub 0. You oftentimes hear me call that H naught. Okay, that's mu equals 39,405. Okay, that's the status quo. And then the alternative hypothesis, labeled H1 or H sub A, that is what is indicated by the text. Okay, can we conclude that the average starting salary of all college grads is increased? So is it the fact that mu is actually greater than 39,405? Okay, so that's our null and alternative. Okay, then step 2 is to determine which distribution to use. Like I said, If you know sigma, in this case, we do know sigma, right there. Sigma is listed right there. Population sigma, okay? Since we know sigma, we can use the z-table. If we didn't know sigma for our class, we would be using the t-chart, okay? Step 3 would be to draw the null model, okay? Again, usually alpha is given in the problem, or in the text. I kind of just gave us a sample alpha right there. Okay. Step 4 was then to calculate our test statistic, our observed z-value, and that's found just like we've always calculated. Z-values x bar minus mu divided by the standard error. We found that z is 3.2, which means a average starting salary of $41,250 is actually 3.2 standard deviations above the mean, which is 39,405. That we calculated the probability of obtaining a z-score of 3.2 or higher given the null model. We found that probability was 0.0007. Okay. Then we came down here and made a decision. Now again, here is the criteria for making decisions. If the p-value is less than alpha, you reject the null hypothesis. Okay? Or another way to think about it is if the z observed or the z obtained is greater than the critical z-value, you reject the null. Okay? I guess the other side would be the opposite conclusion. If over here, if p is greater than alpha, you fail to reject. So I guess we didn't go about that because we didn't have that conclusion. If p is greater than alpha, we fail to reject. Of course, that's the null. You're only ever rejecting or failing to reject the null hypothesis. You're never directly testing the alternative. You're always testing the null. And also, we could say if z observed is less than z critical, then we would also fail to reject. Now, why would that make sense? That makes sense because that would mean you're close to the mean. And if you're close to the mean, just a little bit higher or just a little bit lower, then that happens pretty often. Remember, according to the empirical rule, if you're within within one standard deviation of the mean, you have a 68? No, not 60. Yes, 68% of the data is are within one standard deviation of the mean. 2 standard deviations, you have 95.54% of the data, or so 0.9544 amount of area centered around the mean. So if you were close to the mean, then that would just be normal. That would be typical. That the sampling error, that is error just due to random chance because you're taking samples of size 40 instead of samples of size population, that you would expect some variation. But in our case, we got a z-value of 3.2, which means the sample of 40 we got was 3.2 standard deviations above the mean, which is a very, very unlikely result, again, if we assume the null model to be true. Since that's so unlikely, we conclude, again down here, that the null model does not accurately describe what is going on, so we reject the null hypothesis. So we reject the null hypothesis, and it appears that the alternative hypothesis is does a better job at explaining whatever phenomena is going on here. Okay? All right, again, that was a one-tail test. One-tail test, we'll go into another example of a two-tail. This was specifically a one-tail right-hand test. Later on, we'll go into maybe a two-tail test, and maybe we'll do an example of a left tail test. Although left is very, very similar to right, except we're dealing obviously on the left-hand side, but the mechanics are very similar. So, at any rate, we'll continue talking about this next week in class. If you guys have any questions, always feel free to shoot me an email, or of course you can swing by my office at any time.